Okay, so welcome back to the class. Uh, Today we will kind of finish Rudin's first chapter, and we will go a bit slow today also. We will do two results today. And what did we do last time? Last time we uh, discussed a few things about homotopy, and we proved that two close paths are homotopic, then they are homologous. And I think we also did the residue theorem. And today we will see two applications of the residue theorem. That's what we will do today. Okay, so let me start sharing the screen. You can see the screen. One of you can confirm.
Yes, I can see it.
Yeah, okay. So I hope everybody can see the screen. So today is lecture 9, and yesterday I noticed that it's also September 9. So uh, nice coincidence, and I will have an occasion to talk about dates sometime during the lecture also. Okay. So today's topics will be argument principle and Rouché's theorem. Ariman, can you tell me in 412 you have done Rouché's theorem?
No, we did not do that.
No.
No, okay, okay. Or maybe you might have done without the name. I don't know. Anyway.
No.
Okay.
Like I remember, no, we didn't.
Okay. And argument principle?
He had mentioned it, but we did not derive it.
Okay. Anyway, it's very easy, both these things. Very easy and very nice. I like this topic. So let's do this. So we will go a bit slow, and we will just do this, and we will have time for discussions at the end if you have questions. Yeah. So these are the topics. So in the last lecture, we first proved homotopy implies homology. So very quickly, let's recall. Maybe I will need your help because it was a few days back. Yeah, so we had defined homotopy even in the one class before that, and we wanted to show. So homologous means what? Two curves are homologous, two paths are homologous if for every alpha outside your region omega, the index of alpha with respect to gamma 1 equal to index of alpha with respect to gamma 2. That is homologous. Two things are homologous. And we wanted to show homotopy implies homologous. And the idea was, before that we had made one observation, which is that if you had two curves, this observation is going to play a role in today's lecture also. So let's recall that. What was the observation that we proved? If gamma 1 and gamma 2 are two paths, and if alpha is any point, any complex number, such that if the distance between gamma 1 and gamma 2 is strictly less than the distance between alpha and say one of those curves. So let's say gamma 2 minus gamma 1, the distance is strictly less than the distance between alpha and gamma 1. Then you can show that the index of alpha with respect to gamma 1 equal to index of alpha with respect to gamma 2. And homotopy implies homology was a corollary to this observation. What did we do? So two things are homotopic. So you have this continuous map HST connecting one to the other. At time 0, it is one of those. At time 1, it is the other one. And we can transfer this indices information via finitely many steps. And the way we thought about it, we could transfer it via, this curves coming from H. There was a small problem with that approach because H was only continuous, not piecewise differentiable. But we adjusted for this deficit by taking polygonal paths and applying. So we constructed n number of polygonal paths. The choice of n coming from choice of n coming from, the uniform continuity of the function h, and we had carefully chosen, there will be an epsilon naturally coming, and depending on that you choose an n, and then you divide into n parts, and from one part to the other you can transfer the information on indices, and finally you can transfer all the way, and this was basically the proof of homotopy implies homology. So the main observation was if between two paths the distance is less than alpha and the path. So what I mean is gamma 2s minus gamma 1s, the distance is strictly less than alpha minus gamma 1s for all s in 0, 1. Then the index of alpha with respect to 1 is the index of alpha with respect to the other. We did a little bit more work. You may not be able to transfer from one to the other immediately, but via finitely many steps we could transfer, and we got this result. And then we discussed the residue theorem. And residue theorem, what was the main point? We wanted to say that if you have a meromorphic function and you consider its set of poles, and if you take a path or a cycle, finite sum of paths, which should not go through these poles. So take your cycle in omega minus the set of poles. So if you have a cycle there, and assume it is homologous to 0, because it's a corollary to the global Cauchy theorem. So assume it's homologous to 0, then the integral 1 by 2 pi I integral of fz dz over the cycle is summation residue at each pole times the index of that point around gamma, and sum over all the poles. And the observation was that this would be a finite sum. This would be a finite sum. There may be infinitely many poles, but this would be a finite sum because basically in the unbounded component indices are 0, index is 0. Therefore, index is 0 for most of these points. Index is 0 whenever it's in the unbounded component. In the bounded component, because poles will not have limit points, it's a finite set. So only a finite sum comes in the picture. And this was the thing. So to which function did we apply Cauchy's theorem? So if you have a finite set a1 etc. an, you can take the principal parts q1 etc. qn, and we considered the function f minus q1 minus q2 etc. that function, and applied considered it at the right set, and applied the global Cauchy theorem. Because we had the assumption of homologous to 0, it was straight away applicable, and that's how we proved the residue theorem. So we have quickly recalled both the things, and today we will discuss two applications of the residue theorem. One is what is called the argument principle, and the other is Rouché's theorem. And discussion session will be at the end. I think this is a better format, so that we will cover what we want to cover, and then we will have free time for discussions. And no specific agenda. You can ask questions, we can discuss whatever we want to have. Yeah, this reminds me, I have quickly looked at so we had the quiz, and all of you have responded. I randomly looked at a few things, though I did not evaluate, which I will do today or tomorrow. So you will get an email saying these are the marks that you have got, and if you click view, you may see my comments if I have commented. If there's nothing to comment, I will not comment. Otherwise, I may make some comments. So this will be soon. Anyway, you will get an email notification. And I must tell you that unlike the quiz 1, I am very happy with all of you in quiz 2, because most of you have answered. Answered in the sense, I did not expect a complete answer with full proof anyway. I just wanted the picture in your mind, and most of you have got it right. And most of you have also mentioned the source, etc. So I am happy. This is all that I want. Be honest about your source. Some of you have just said source is internet. That's not good enough. Please say which. Just copy the web link also. Just don't say internet, Google, etc. That's too vast. Okay. So for next time, but this much is progress, and next time you actually tell me what the source is, not just Google or internet. Okay. If you have used, if you have done yourself, of course you will not say what your source is. Okay, so and there will be one more question which will come up in the slides. So that also you have to do, and we will discuss in the discussion session when the deadline will be. It's just one simple question, so I will not give too much time. Let's discuss during the discussion session. Yeah, question will come up during the slides. Okay, so. Argument principle, let's start, and then we will do Roche's theorem, which is an immediate corollary to the arguments principle. So let omega be a region, and let gamma be a closed path in omega, and let f be holomorphic throughout omega. And you consider the function, what is called the logarithmic derivative, f prime divided by f. F is holomorphic, consider its derivative f prime, and divide by f. What can you say about this function phi? It is a meromorphic function in omega. Why is that? Why is this meromorphic? Because f may have a number of zeros. So if f has a zero at a point A, you can write f as z minus a to the power something times a function h. And h is holomorphic and h is non-vanishing in a neighborhood of A. So in a neighborhood of A, if you take 1 by f, that will be of the form a holomorphic function divided by z minus a power some m. So this shows that it is a pole of order m at A, and it's isolated because h is holomorphic throughout. So 1 by f is meromorphic if f is holomorphic. F prime is anyway holomorphic, so f prime by f is meromorphic. Okay, so this is a meromorphic function, and yeah, so this is coming in the slides also. If A is a zero of f, it will come with a finite order. This we had observed long back because of power series representation. Any zero will come with a finite order. So call that m. M is called the order of the zero or the multiplicity of the zero. And you can write fz equal to z minus a power m times hz, where on a neighborhood, h is holomorphic and non-vanishing on some neighborhood V of A. There is a small neighborhood V of A where h is holomorphic, because h is holomorphic anyway because h is holomorphic everywhere. You know, it's a remaining part of the power series. So that's holomorphic everywhere, but it's also non-vanishing on a small neighborhood of A. Why is that? Because if h vanishes at A, then the multiplicity, then z minus a will come to the power of more than m. That's not possible because m is the order. So h does not vanish on A, and therefore by continuity it will not vanish on a small neighborhood of A. Okay, so such an h you get, and m is the order or multiplicity. Now on v minus a, you can consider this function phi, right? Only at a there's a problem. On v minus a, you can consider phi. It is f prime z by fz, and fz is of this form. So you take f prime z, right? F prime z is z minus a power m times h prime z plus hz times m z minus a power m minus 1. Divide by fz. So what will you get? Quick check. You will get f prime by f equal to m by z minus a plus h prime z by hz. Now remember, on V, h prime z is holomorphic everywhere. Hz is also holomorphic everywhere. So, and h is not vanishing on V. H is not vanishing on V. So h prime by h is holomorphic on V. H prime by h is holomorphic on V. And m by z minus a makes sense on V minus a. So you have got phi to be this. So phi has a pole at A, and it is a simple pole. And what is the residue? Residue of phi at A is m, right? Because this part is holomorphic in a neighborhood of A, so that doesn't contribute. So the residue is exactly m. We are going to apply a residue theorem to this phi. So in order to apply residue theorem, you need a cycle which is homologous to 0. We are going to apply residue theorem to gamma. Gamma is a closed path. That's not enough for me to apply a residue theorem. So assume from now onwards that gamma is homologous to 0. And is that enough to apply residue theorem to phi? because residue theorem, you needed the cycle to be homologous to 0. You also needed the cycle not passing through. You also needed the cycle not passing through any of the poles. So A is a pole. So you will assume that gamma is homologous to 0 and that F has no zeros on gamma star. Why do you assume F has no zeros on gamma star? Because if F has a 0 on gamma star, then phi has a pole on gamma star. So gamma is passing through a pole. That you wanted to avoid in order to apply residue theorem. Right? So assume that F has no poles on gamma star. So that gamma is via omega minus the poles of phi, and assume it is homologous to 0. Under these two assumptions, you are in a situation where you can apply the residue theorem to phi. So apply the residue theorem to phi. What will you get? You will get you can take the zeros. It may have all the zeros, and all those zeros will be the poles. And at each pole, the order of the zero is exactly the residue of this function at that particular point. So applying residue theorem, you will get this to be summation residue times the index. This is a set of poles. Set of poles of phi is nothing but the set of zeros of f. Set of poles of phi is nothing but the set of zeros of f. So this is what you get. And what is residue of phi at A? It is the multiplicity MA. So you get this identity, summation MA index of A with respect to gamma. This is what is called the argument principle, but argument principle may be the standard terminology is for a very simplified case of this. So what we will assume is, so in order to state the classical argument principle, assume gamma is such that it is homologous to 0. So if alpha is outside omega, you know that the index is 0. What if alpha is inside omega? If alpha is inside omega, alpha may be on gamma star or outside gamma star. If alpha is on gamma star, index is not defined. Okay, index is defined only for points outside gamma star. So assume that the index inside omega is always either 0 or 1. So you're basically taking a simple closed curve. So if the point is inside, the index is 1, and if the point is oriented correctly, so if the point is inside the curve, a region bounded by the curve, it's 1, and if it is outside, it is 0. That's what you're assuming. So basically a simple closed curve. So alpha and omega minus gamma star. So then what will happen? This may vanish at many points, and otherwise it is just 1. So this summation is just summation MA, where A are exactly the zeros where the index is 1. In other words, you are looking at zeros inside the simple closed curve. You have a simple closed curve gamma, and if A is a 0 strictly inside, then the index is 1. And there, you count it with multiplicity. So that is what is called the argument principle. So number of zeros of f counted with multiplicity where inside the curve, in the region bounded by the curve, that is exactly, so that I denote by n subscript f, it is 1 by 2 pi I integral phi z, but phi is f prime by f. So it is this thing. This is what is called the argument principle. So it has a very simple proof. It just follows from a quick application of the residue theorem. Okay, is the proof clear? Statement clear? Now there is one more way of writing this, because what you observe is, so I haven't done it in the slides. I would like you to check. It's a simple check using one variable calculus. What is f? F is a holomorphic function on omega, and what is gamma? It's a path taking values in omega. So gamma is from closed interval 0, 1 to omega, and f is a function on omega. So f compose gamma is another curve, another path. F compose gamma is another path, and you check what is the index of 0 with respect to f compose gamma. So index of 0 with respect to f compose gamma will be integral over f compose gamma dz by z. And you can substitute and you will get exactly this integral. So This is called the argument principle. Check that this integral is nothing but index of the point 0 with respect to f compose gamma. See, we are not saying anything about 0 being in the region or not being in the region, etc. In order to make this statement, that's not important. This is like, when we constructed those polygonal paths, whether they belong to omega or not, it doesn't matter. Similarly, where 0 is, I don't care. You are just computing the index of 0 with respect to f compose gamma. And you can apply the definition integral over f compose gamma dz by z and expand, substitute, put it back. You will get exactly that integral 1 by 2 pi I integral f prime z by fz over gamma. So the argument principle says that if you have a simple closed curve, the number of zeros inside is exactly of a holomorphic function f is exactly the index of 0 over f compose gamma. This is the argument principle. And now the same proof, the idea of the proof works more generally. If f is given to be only meromorphic, not holomorphic, but meromorphic, what will happen? Then you may write f as h by g. Both h and g are so maybe I don't know this, no? Yeah, I did not pay attention. I assumed that. So okay. Anyway, let's state it because the statement is correct. So in the proof, what will happen is okay. Let me not say it is meromorphic. Let me say that it is of the form holomorphic by holomorphic. I don't think we can show now that a meromorphic function is of the form holomorphic by holomorphic, which is true, but I don't think we can do that right now. That will take time. So let me make the generalization as follows. It turns out to be meromorphic, exactly meromorphic. Suppose instead of f you have f by g. Both f and g are holomorphic. Then the same proof will work, right? If g is of the form 1 by f, you will get it will be a pole, and when you do this thing, you will get minus m by z minus a with m positive. You will get a minus sign because it will be in the denominator. So you check this. If it is of the form f by g, so if f is given to be only meromorphic, so once again, I did not think so much yesterday when I was typing. Meromorphic, assume for the moment that you know that meromorphic is of the form f by g, where f and g are holomorphic, which we will prove later. So assume that. So if f is given to be only meromorphic, the same proof will give you that that integral 1 by 2 pi I integral f prime by f is number of zeros counted with multiplicity minus the number of poles counted with multiplicity. Because in the residue now, for whatever is in the denominator, the residue will come as a negative number. So it will be minus the number of poles. Slightly more generally, I saw this on Wikipedia and proof is the same. So I have stated it here. If f is meromorphic and g is holomorphic, and if you don't assume simple closed, etc., you will have to throw in the index also. You can get integral gamma f prime by f times g. If this g is analytic, this will be summation over the zeros of f counted with multiplicity, g evaluated at a, and the index. Index came in our proof. We had a simplifying assumption, it is simple close. Now we are not assuming that for the statement. Minus over poles with multiplicity GB index B. Same proof works, but you write it down once more on your own. Okay, so this is more general form. G equal to 1 and simple close was the argument principle. Okay, so this was.
So,
yeah.
for the meromorphic part,
Yeah.
we know that given any pole there, we can write it as locally, we can write it as f by g, right, for holomorphic functions by clearing the denominator.
Okay, I was a bit confused. So if it is meromorphic, then it has some pole. Yes, and then what are you saying?
So there we have this. There's this principal part.
Correct. And yeah,
there
Yeah, locally, yes.
Locally we can do that.
Already know, and local is enough for proof, right? We were arguing only on V minus A, no? Yes, yeah. Good, good, good. So yeah, so the statement is okay. Even with meromorphic, our proof was no. Is it fully okay, Ariman? Because at one pole, yeah, I think it's okay because at every pole, locally it is of that form. But is that enough? Because aren't you using globally it's of the form f by g? Because at one pole you will do that analysis. But see, finally my left hand side is f prime by f for the same f, no?
Yeah.
So by clearing this denominator, etc., you will write it as f by g locally, but at some other place it may be f prime by, I mean, f1 by g1, no?
We can, once we evaluate, we just have to find we just need the residue at that point, right?
Correct. But
we'll apply the residue theorem to begin with on the mero. Like, can you go back one slide?
Yeah. Maybe
yeah,
one.
here. No, here itself. Yeah, here. So
no,
here what we have in the first equation.
Yeah.
The first equation still holds true, right?
First equation is general.
I
because
mean,
yeah, function.
Removing the rightmost side. Yeah. This part is general, right?
Yes, this is for any meromorphic function phi. So if suppose phi is our meromorphic function, this is true. And but I will say over all the poles, which is same as this. Yes, this is true. No, no. I mean 0 of f is not correct now. It should be 0 of f union. It should be poles of phi.
Poles of phi. Yeah.
Of phi.
And for each phi, we can locally get the residue to be the multiplicity of the 0 or the order of the pole with a negative sign.
Locally, yeah, but my question is here instead of 0 of f, I would have liked to say it is over 0 of f union poles of g.
Poles of f.
Yeah, 0 of f. No, you are writing it as.
Okay, yeah. So I want
meromorphic function. Okay, suppose f is your meromorphic function, and phi is f prime by f, right? Phi is f by f, and f is your meromorphic function. So here the set will be zeros of f union poles of f.
So instead of that, I'll just say that it is the poles of phi. That is what the residue theorem will tell me, right?
Poles of phi, yes, yeah.
Yes. And then I will individually calculate each pole separately. And there I'll see that it will just come out to be
the local argument. This is only a local argument is what you are saying. Yes. On V minus A. At a given 0 you will do this, and at a given pole you will do this. And you can do the same thing for, so at a pole you will do this, and you will get it with a negative minus m where m is positive, right?
Yeah.
Yes. And therefore you can sum up. Yeah, you're right. Yeah, that's good. So you don't need to know that it is globally of the form f by g. This is completely a local calculation. So this is fine. Good. Yeah, thanks. Yeah. Anyway, since a topic came up, let me say that this also we will do that globally itself. It's of the form f by g. And sometimes it's good to remember the words. It's a corollary to what is called the Weierstrass theorem. So Weierstrass theorem, we would say that if you give me any set without a limit point, then I can construct a holomorphic function with precisely those that set that you have given me as a set of zeros, and this will be an immediate corollary. We will see when it comes. Yeah, but here you don't need that. Good. So you get this generalization, and now let's do Rouché's theorem. Okay. So I told you, so I thought, no, I mean, this is a nice topic, and Rouchet is not all that famous. So I checked the Wikipedia entry. Of course, Rouché's theorem is famous, and he has one more result about in linear algebra. These are the only two results listed in Wikipedia. So so I can't pronounce all these French names correctly, but I have put the French accents correctly. Eugene Rouge or something, Rouge or something, I don't know. Okay, so this accent is. Does anyone know French in this class? In school or something, you had a little bit of French. Okay, anyway, so on the E, on this E the accent is this way, and on this E the accent is the other way. I think one is called grave and one is called acute. I don't know which one is which. I checked it yesterday, but I always forget. Yeah, maybe this is grave and this is acute. Yeah. I also thought, I will say something about the dates, because I mean this only. When I was copying this from Wikipedia, his birthday is August 18th, and he died on August 19th. So I was a bit curious, and also I noticed that today is September 9th and it's lecture 9. So I got a bit curious and did a little bit of Googling yesterday on dates. So, right, I mean, between the birthday and date of death, there's only 1 day difference. So what would be a natural thing to search for? Who are the famous people who died on the same day? Not even 1 day gap. And there are many such people, and of course there are articles about them on everywhere on the net. So maybe the most famous name that's mentioned there is William Shakespeare, but he was too long ago, and it's not all that clear historically what is the exact date of birth. So there's some ambiguity. But I noticed that there's this famous actress Ingrid Bergman. How many of you have heard this name? Ingrid Bergman. Maybe we have some time, so let me just. I think when I go to something else also, you can see that. No, now you should be seeing my Google page. Is that correct? Whatever I share on desktop, you can see. So let me just. I have searched it yesterday, so it should come. Yeah, Ingrid Bergman. She's a very famous Swedish actress. Have you seen movies of Hitchcock and all that? She has acted in several of Hitchcock movies. Some of my favorite movies actually. So her date of birth is 29th August, and death date is also 29th August. And also there is this famous author. This also I searched yesterday. Yeah, it's there. Betty Friedan. Very famous author. I think feminist author. Her book, The Feminine Mystic, is supposed to be a classic. I haven't read it, but I have heard a lot about it. And hers also, it's February 4th, February 4th. So there are many such people. In fact, there are a lot of articles on that. Anyway, this was a detour. So just for. I mean, in a real class, I think only Onkar was there in my real class, not anybody else from this class. Once in a while, not once in a while, always I like to digress a lot and talk about other things, because it's online mode and slightly more prepared lectures. I don't get so much such opportunity, because most of the digression also should be, kind of extempore. So that doesn't typically happen. Anyway, doesn't matter. I would have liked that a bit more to talk about other things. Anyway, this was one such occasion. Yeah. So note the dates and also note the accents. Accent meaning this, when it's French or some other language, non-English language, many of them, the pronunciation, how you pronounce. So the pronunciation of this E and the pronunciation of this E is, it's different. Yeah. Since I'm not good at pronunciations, I won't even try. Okay. So let's prove it. So suppose you have gamma, a closed path homologous to 0 in omega. And assume it's a simple closed curve that the index is either 0 or 1 for all omega minus gamma star. So this is in the context of the argument principle that we stated. We will get number of zeros of f counted with multiplicity is exactly the index of f composed gamma at 0, right? This is what we will get. So suppose f and g are in So Rouché's theorem, you want to conclude about number of zeros inside a curve based on number of zeros inside a curve of another function. You want to compare the number of zeros of f and number of zeros of g. Okay, and it will have many beautiful applications. So suppose f and g are in h omega, and also assume that f has no zeros on gamma star. Okay, this much you assume. Right, this was an assumption in my argument principle, so I am assuming that because I'm going to apply argument principle. And assume that, so this is the hypothesis of original version of Rouché's theorem, that mod fz minus gz is strictly less than mod fz. Where is this? This is on the curve, on gamma star. Okay, so on the boundary, on gamma star, you have this strict inequality. So this should remind you of what? This should remind you of that observation that we had. Gamma 2 minus gamma 1, distance is strictly less than alpha minus gamma 1. When I don't have an alpha here, what is the meaning? Alpha is 0, right? So 0 minus fz. So this is happening on gamma star. Then the claim is the number of zeros of g equal to number of zeros of f. This is Rouché's theorem. So if you have in particular a simple closed curve and you want to count how many zeros f has inside that, suppose you can construct a nice function g with this property on gamma star, the strict inequality on gamma star, and g is so constructed so that no number of zeros of g inside that gamma is obvious. Then you would have concluded something non-obvious about the number of zeros of f. This is how it will be used. Okay, so what is the proof? Proof is very easy. It's argument principle. So we have already proved argument principle says that nf is index of 0 with respect to f composed gamma. And note that from this condition g cannot vanish on gamma star. What happens if g vanishes on gamma star? You will get mod f is strictly less than mod f. That cannot happen. Therefore g doesn't vanish on gamma star. Therefore argument principle is applicable to g also. So therefore you will get ng equal to index of 0 with respect to g composed gamma, and I claim that this finishes the proof. You are done. NF equal to ng. Why? Can one of you tell me? Proof is done. Why? You want to show NF equal to ng, so you want to show this index equal to this index. Now that is true. Because you know that gamma 1 and gamma 2 alpha will have the same index if mod gamma 2 minus gamma 1 is strictly less than mod alpha minus gamma 1. So this is at 0. So this is 0 minus f of z, and this is fz minus g of z, where on gamma star. So if you consider the curve f composed gamma and g composed gamma at s is in 0, 1. So gamma of s is in gamma star. So f composed gamma minus g composed gamma, the modulus is strictly less than 0 minus f composed gamma for all s. So it's exactly that condition. Therefore, the index of f composed gamma at 0 is equal to index of g composed gamma at 0, saying that ng equal to nf. So that's the proof. Okay, so this is Rouché's theorem. So Rouché's theorem had this assumption that the function that is coming on the left side and the right side, right? It is not so easy to remember. In fact, I always forget this statement because you have f coming twice on both sides and g coming only here, and there was a technical condition on f. The technical condition on g was automatic. So f has no zeros on gamma star. There is a stronger version of Rouché's theorem. So this is what Rouchet stated, and this is the proof. It comes from argument principle. In fact, we can prove a stronger statement, and based on similar ideas. And this is there in Wikipedia, and this is there in some other textbooks also. So Wikipedia says Conway has this statement. I did not check. So it refers to the 1962 book on complex analysis by a mathematician called Theodore Esterman. Wikipedia is not saying he proved this. It is certainly there. So it was certainly there before 1962. Rouchet was long back. No, Rouchet was when 1832 to 1910. So certainly before 1962, this stronger version was known. Again, a digression. Esterman is a number theorist, analytic number theorist, and his student, one of his students, he had many famous students. One of his students was a Fields medalist, Klaus Roth. And I am stressing this name because though he is a number theorist, there may be an occasion for us if we have a lot of time. I don't know how fast we are going or how slow we are progressing. If we have covered everything in the syllabus and if we have 1 or 2 lectures left, we may do something outside syllabus, and then we will have occasion to mention Klaus Roth. The word to remember, suppose I don't have time, and if you are interested, the word to remember is what is called Nevanlina theory. So there is something called Nevanlina theory, which I don't know really much, but basically it says that many results in complex analysis and many results in number theory, classical number theory in the sense actually dealing with numbers, have a lot of parallels. You cannot use one to prove the other, but you can use one to guess how a result should be in the other domain. So there's a dictionary between complex analysis and number theory. And sometimes, there may be a famous result in complex analysis, and you can formulate via this dictionary, you can translate, and you can get a statement, and then you can prove it in number theory. And the other way also it might work. You may have a famous result in number theory, and via this dictionary, you can formulate a result in complex analysis and prove using methods of complex analysis. So this is what is called Nevanlina theory. Nevanlina is a Finnish mathematician. By the way, he is the advisor of Alfors, the famous book by Alfors, which we had mentioned earlier. Alfors is also a Fields medalist, right? Alfors is the first Fields medalist, 1936, and Klaus Roth, I think, 1958. Okay, so what is this version? Gamma is as before. Let's assume gamma is simple closed. So it's homologous to 0, not just that, for any alpha in omega minus gamma star, the index is either 0 or 1. So it's either inside, gamma is positively oriented, or 0. So gamma is as before, and we don't need to assume, so this is better. We don't need to assume that f doesn't vanish on gamma star. I'll get it automatically from my condition. Okay, f doesn't vanish on gamma star, I don't need to assume. This version is not just stronger, of course it is stronger, but it's also easier. It's both stronger and easier. Easier meaning easier to remember, because earlier version had some asymmetry between f and g. Here it is symmetric in f and g, so it's easier to remember. And unlike the original version, so the hypothesis is, even the hypothesis is easy to remember, it is just strict triangle inequality. What is triangle inequality? Mod f plus g is less than or equal to mod f plus mod g. So this is strict. Mod of f plus g is strictly less than mod f plus mod g. Mod fz plus gz is strictly less than mod fz plus mod gz. This is what you need to assume. I can also say mod fz minus gz, right? I can take, instead of g minus g, and I can formulate it like this. So let me formulate it like this. The point to note is that it is strict. Okay. And where is this inequality given? Where is the inequality in original Rouché's theorem given? On gamma star, on the boundary. So same, where? On gamma star, of course. Okay. So Z in gamma star, you have this inequality, and then Rouché's theorem is true. So what is Rouché's theorem? NF equal to NG. Number of zeros of F counted with multiplicity is equal to number of zeros of G counted with multiplicity. This is stronger, no? Because why is this stronger? Because earlier you had to show the inequality mod f minus g is strictly less than mod f. But here you don't have to show that much. This is a bigger number. This could be a bigger number, and you have to show only it is less than this big enough number. Earlier you had to show it as much less. You had to show that it is less than mod f itself. Here you are only showing it is less than mod f plus mod g. So it's a stronger version. And it is easier to remember because now you don't have to bother whether on the right side it is f or g. It is symmetric. It's both. Okay. So how do we prove this? Statement is stronger. So the ingredient in the proof has to be slightly stronger. So the key ingredient in the earlier proof was what? The key ingredient is, in order to compare the indices, you had to show that we use this observation that between gamma 1 and gamma 2, you can transfer the indices information. That's what we used. And you got the original version of Rouché's theorem. So in order to get the stronger version, you make that ingredient that you supply to the proof slightly stronger. So what is slightly stronger than that observation? By that observation, I mean mod gamma 2 minus gamma 1 is strictly less than alpha minus gamma 1. Then index of alpha with respect to gamma 1 is index of alpha with respect to gamma 2. What is slightly stronger than that? Using that many times is stronger than that. And using that many times, what did we prove? Using that observation many times, we proved homotopy implies homology. So using that many times, we proved homotopic implies homologous. So replace the earlier observation with the stronger observation. Homotopic actually implies homologous, and you will get the stronger version of Rouché's theorem. So NF equal to NG follows if we show that F compose gamma and G compose gamma are homotopic. This is enough, right? But if you recall, the proof of homotopic implies homologous. Where was homotopy given? Homotopy was given right. You wanted to show homotopic implies homologous. Homologous meant for all alpha outside omega index are same, and we assume that they are homotopic in omega, and alpha was outside omega, right? So we have to show here. So here we are looking at index of F compose gamma and index of G compose gamma at which point for Rouché's theorem? At the point 0. So you have to be in omega which does not contain 0, where you have to show that these two are homotopic. So you have to show that these two are homotopic in a domain that does not contain 0. Then you can apply homotopic implies homologous, and you will show that these two are homologous at 0. Now homologous in omega which does not contain 0. Therefore index of 0 will be equal. So you have to show that these two are homotopic in a domain that does not contain 0. Then your proof homotopic implies homologous will show that NF equal to NG. Now they are homotopic, that's easy. In fact, you can give the simplest kind of homotopy. You can give straight line homotopy. You can connect F compose gamma and G compose gamma via straight lines joining this. You can give H of ST equal to 1 minus T F of gamma of S plus T G of gamma of S. At T equal to 0, the curve is F compose gamma. At T equal to 1, the curve is G compose gamma. The observation is none of these curves at no point, at no time t, HST passes through 0. That's all that you need to observe, and that is observation. Note that at no time t, HST passes through 0. Why is that? Can one of you tell me? These curves, whatever t you take, this curve will not pass through 0. Suppose it passes. Yeah.
Yeah, then we could apply the triangle inequality, and that would get violated.
It will get violated. So if it passes through 0, then you will get 1 minus t times F equal to minus Tg. So you will get F equal to minus t by 1 minus t times G, and F is a negative multiple of G, and F is a negative multiple of G is not possible under this thing. That's why I put minus G here. If I had put a plus G, then I would have had to argue with maybe I should have taken my homotopy to be with a minus sign here or something. Yeah, so triangle inequality will get violated. So therefore everything is okay. So you have proved the stronger version. I like this example from Wikipedia because it uses that 31 is strictly less than 32. So of course you can take any two numbers and you can cook up such a polynomial, but this is already there, and So let's see, this is a standard application. You take the polynomial z power 5 plus 3z cube plus 7. So of course it is cooked up in such a way that this number comes there. And you take the disk mod z is strictly less than 2. And the claim is that this polynomial, see such a polynomial, anything beyond cubic or something, finding roots is not easy, right? In fact, anything beyond quadratic is not so easy. Cubic, maybe you will do some trial and error, but other than that, it's difficult. But you're going to claim that this polynomial has exactly 5 zeros inside the disk mod z less than 2. Why is that? Rush's theorem. So on mod z equal to 2, if you take the curve mod z equal to 2, mod z strictly less than 2 is inside that region. And you consider the polynomial 3z cube plus 7. So 3z cube plus 7 is f minus g, where f is this and g is z power 5, right? F is this polynomial and g is z power 5. So this is f minus g. So modulus of f minus g, where should you check? You should check on gamma star. So on mod z equal to 2 by triangle inequality is less than or equal to 31, right? 3 times 8, 24 plus 7, 31. 31 is strictly less than 32, which is mod z power 5. On mod z equal to 2, 2 power 5 is 32. Therefore, you conclude that f and g have the same number of zeros inside this. But z power 5 has how many zeros inside the disk? All its zeros are 0. And at 0, it is multiplicity 5. So it has 5 zeros inside. Therefore, this polynomial has 5 zeros inside. This is a standard application. Okay. So it's a very, very beautiful, powerful theorem. Simple proof, simple theorem, elegant, but very nice. So you can conclude many such things using Rush's theorem. Okay, here is the next quiz. It's again, it's as simple as this. So I mean, I'm not giving you a difficult question at all, but to keep you engaged and to make you do some problems, here is the assignment. You consider the equation e power z minus 2 z power n equal to 1. And the question is, how many solutions does this equation have in the open unit disk? Depending on your roll number, you have to choose the n. N is the last 2 digits of your roll number, and you have to give me your answer. Okay, so each of you will get different answers. And again, as our standard procedure on Google Forms, so I'll create the Google Forms and I'll send you the link on WhatsApp. And if you have difficulty in accessing, respond in the WhatsApp group itself. But now that we have done twice, there should be hopefully no problem. Let's see. And the deadline will be tomorrow 12 noon. Okay, so I will do it after this class. I will put the quiz. Deadline will be tomorrow 12 noon. I'll close the format tomorrow. Okay, so the question is clear. Okay. Here is another example which I got from this particular paper. Show that this particular polynomial z power n times z minus 2 minus 1 has typo. I should not have put a full stop here. Has n zeros in the open unit disk. Okay, so this is what you have to show. And one root in the interval 1, 3. This of course is easy, right? I mean, at 1 you can check it's negative, and at 3 you can check it's positive. Maybe even at 2 it is negative. So there is one root between 2 and 3 actually, but I have written 1 deliberately because I'm interested in saying that there is one root bigger than 1. Okay, it so happens that it is bigger than 2, but it's bigger than 1 is what I'm interested in. And all the others, so this will have n plus 1 zeros, right? And n plus 1 roots, and one root is bigger than 1, strictly bigger than 1, and all the other roots are strictly less than 1. Okay, so you have to show that this has n zeros. So you can apply Rush's theorem, take gamma to be the unit circle, and take gz to be z power n times z minus 2. So that f minus g is minus 1. Okay, so mod fz minus gz is 1. And what is mod gz? Mod gz on mod z equal to 1 is mod z minus 2. And that is bigger than 1 everywhere except at z equal to 1. At z equal to 1, you can't show strict inequality. At z equal to 1, mod z minus 2 is 1, and you can't get strict inequality. You are getting 1 equal to 1. Whereas to apply classical Rouché's theorem, you need a strict inequality throughout the boundary, which you are not getting. Therefore, this is an example where you can't apply the original version of Rouché's theorem. But you can apply the stronger version of Rouché's theorem, because everywhere this is true, and therefore if you add mod fz also it is true, and at z equal to 1 this is 1 and this is also 1. But what is f of 1? F of 1 is minus 1 minus 1 minus 2, therefore modulus of f of 1 is plus 2, so you're adding plus 2. So strict inequality, strict triangle inequality is true throughout, and therefore you can apply that Rouché's theorem, the stronger version, and you can conclude that nf equal to ng. And note how many zeros this has on mod, inside mod z less than 1, z equal to 0 n times, and this has no 0 because this 0 is 2 which is outside. So this is exactly n zeros inside the open unit disk, therefore this has n zeros inside the open unit disk. You can also check that all the zeros are distinct. That's not Rouché's theorem, that's some other check. If you're interested, you check that also. What you do is you take the derivative of this and look at the zeros of the derivatives, and you check that none of those points is a 0 for f. So there's no 0 of f where the derivative also vanishes. So they're all distinct. There's no multiplicity. All are distinct zeros. Okay. So the reason why I stressed it's bigger than 1 is, these are famous numbers. In fact, this is the second time I am introduced. I can take an Indian name, Vijay Raghavan. Do you recall when did I have an Indian name in this course before? Can someone recall? I think this is the second time we are taking an Indian mathematician's name. When was the first?
I think when we spoke about the books.
Yeah. Do you remember the name? Is this Chirag? On the screen, I can't see the names.
Yes, sir. This is Chirag. Yeah.
Good. So I'm able to recognize by voice. Yeah. So do you remember the name?
No, sir, I don't.
Someone else remembers the name?
Sir, Raghavan
I think it was something like Narasimha.
This is this. One is Ariman and the other was Mamta. Was it Mamta or?
Sir, it was Suhasini.
Suhasini. Okay. Yeah. See, what happens is on the screen, unless I am on MS Teams, I can't see the name. So though I mean, when I check the video later, there the names are there. So I don't know why I can't see. Okay, Suhasini, yeah, good. So we had 5 books: Alphonse, Rodin, Conway, Narasimhan, and Gamlin. Yeah. So Narasimhan, and this is Vijay Raghavan, T. Vijay Raghavan. So what is a Piso Vijay Raghavan number? I don't think they thought about this number. It is some other name I saw in Wikipedia yesterday. I'm forgetting. But these two people studied these properties of these numbers a lot, and therefore the number is known as Piso Vijay Raghavan number. It is such a number, what is called an algebraic integer. What that means is you take a polynomial with integer coefficients, all the coefficients AIs, right? Polynomial x power n plus an minus 1, x power n minus 1 plus etc. All the coefficients should be integers. So it's a polynomial of order n, so it will have n roots in complex numbers. And suppose one root is strictly bigger than 1. And that strictly bigger than 1 number is called a Piso Vijay Raghavan number if all the other roots of this polynomial have modulus strictly less than 1. So suppose you have one root whose modulus is strictly bigger than 1. It need not be a real number. The modulus is strictly bigger than 1. And all the other roots of that polynomial with integer coefficients. That's important. Coefficients are integers. And all these other roots have modulus strictly less than 1. So these numbers, I don't know much about these things. I haven't read. But these are supposedly important in various applications, various parts. You can check Wikipedia or Google it. And so what we have shown here is, by Rouché's theorem, what we have shown here is this root which is bigger than 2 is an example of a Piso-Vijayaraghavan number, because this polynomial has all integer coefficients. Coefficients are -2 and -1, so all integer coefficients. And this number is a Piso-Vijayaraghavan number because all the other roots of this polynomial have modulus strictly less than 1. Okay, so named after Charles Piso and T. Vijayaraghavan. Okay. Let's stop and have the discussion session after one exercise. So this is not an assignment. This is not a quiz. I'm not asking you to give me your answer, but you work this out because it's nice. I'm making a small change. Instead of z power n z minus 2 minus 1 here, I put z power n z minus 2 plus 1. And show that this has n minus 1 zeros in D01 and 1 root in 1, 2. 1 root in 1, 2 is clear. At 1 it is negative and at 2 it is positive. And n minus 1 zeros in D01. So 1 plus n minus 1 is n, whereas this will have n plus 1 roots. What is the other root? That's obvious. 1 is a root. Because when you plug in 1, it is minus 1 plus 1 is at 0. So one root is 1. Another root is strictly bigger than 1, and n minus 1 zeros in D01. So this root in 1, 2 is also an example of a Piso-Vijayaraghavan number. No, that is not an example, because all the other roots are not, modulus is not strictly less than 1. Whereas one root is equal to 1. But from that you can't conclude that's not a Piso-Vijayaraghavan number, because you can factorize this, take z minus 1 out and take the other polynomial in degree n. Observe that that also has all integer coefficients, and therefore this number is a Piso-Vijayaraghavan number. So you can't conclude it from this polynomial, but from that polynomial. Yeah. So maybe earlier itself I could have said, take the minimal polynomial of the number, meaning the least degree polynomial with integer coefficients which is satisfied by this number. All the other roots of that polynomial should have absolute value less than 1. That's a better thing. And then this has, yeah, so this is also a Piso-Vijayaraghavan number, because if I take z minus 1 out, the other one also has all coefficients integers. So this also is a Piso-Vijayaraghavan number. Anyway, that's not our point. Point is to show that this has n minus 1 zeros in D01. So straight away, if you take mod z equal to 1, it looks like neither the original version nor the stronger version of Residue theorem will apply. Because what happens is at 1, yeah, you have to check. So I think, so I haven't really looked at it, but I think this requires a new idea. So you try it yourself. If you don't get after spending enough time, here is a reference. So there's a beautiful answer here, which requires a new idea. It is Residue theorem, but with a new input. Okay, so check that out. So we will stop here and we will have the discussion session for some time. So I can stop sharing. Yeah. So okay, good attendance. 20 students are there. So let me check who are not there. Of course, I don't remember all the names, but Chirag, you were not there last time, no?
Sir, I was there, sir. Like, I was not there at the end, I think, because I wasn't there at the end only.
But I downloaded the attendance list and I thought I did not see your name.
No, like I saw the video again, like see the video again, sir. I'm there yesterday. Like the last class, I was there.
No, I mean, it's okay, but my genuine doubt is attendance sheet, attendance list. If your name is not there, that means attendance list is not correct, no?
I think it only takes people who are there at the end or something. I don't know, because I was not there at the end.
There was somebody else. It was written, he left earlier. So I think leaving early is okay. It's recording all the joining and leaving. In fact,
September 5th.
Say that again, Chirag.
So was it on September 5th? Was it the class on September 5th?
Yeah, very last class. So September 5th only.
I was there. So I was there.
Okay,
you can see it
good.
in the video.
Yeah, no, it's fine. Yeah. So today, who are not there? I think our class strength is 23 and 20 students are there. So Rahul is not there because it says suggestions Rahul. So Rahul is 1. Who else? Okay, anyway,
The
let me
last class
download.
was
You
September
can see it
4th,
in
by
the
the way.
Last class was
September 4th.
yeah September 4th. I was there.
September 4th, Friday. Yeah.
And you can see the people
so
who are invited on the screen who have not come. So you can see all their names.
But all the names are like this. All the names may not be there on the screen. No, if names are, I think the screen can have only 3
No.
plus 3 plus
There's
4.
others invited, and you can see those who are invited who are not here.
Okay. Anyway, I mean just to know the technicalities. So let me download this attendance list also. I will check later. Oh, by the way, I should stop this recording. Yeah, I should stop this recording and start the new.